In this video, we're going to cover sections 13.1 and 13.2, at least the first part of it, where we're going to get some sketches of vector-valued functions. So the first thing we want to do is we want to talk about a vector-valued function. So a vector-valued function, or a vector function, is a function whose domain is a set of real numbers and whose range is a set of vectors. So we get r of t here is equal to some real valued function x of t in the first coordinate, a real valued function y of t in the second coordinate, and a real valued function z of t in the third coordinate. Using our other notation for vectors here, that's also x of t I plus y of t j plus z of t k. So again, what this means is that we just have a vector-valued function is, for a three-dimensional vector-valued function, is three real-valued functions, one function for each of our coordinates. So let's take a look at this first example. We are going to try to sketch this graph defined by the vector function r of t is equal to t, 2 minus t, 2t. Well, we might recognize this as a linear equation in three dimensions, i.e. a line. The first thing I want to do is I want to introduce this idea of parametric equations. We've used that when we talked about lines in the past in section 12.5, but we're going to discuss that a little bit more now because it's going to be pretty important from here on. So, our vector-valued function r of t is t, 2 minus t, 2t. In other words, x of t is equal to t, y of t is equal to 2 minus t, and z of t is equal to 2t. So that is our parametric equations for this vector function. So when we say parametric equations, that means we take our vector function and we write each of our coordinates x, y, and z in terms of a single variable here, in particular that single variable t. Okay, really parametric equations just means we rewrite the function in terms of a different set of independent variables. But for right now, that means we are taking our vector-valued function and rewriting each of its coordinates in terms of a single independent variable t. Okay? So, what is this? Well, this is the equation of a line, right? This looks like our parametric equations for a line. X is equal to t, y is equal to 2 minus t, z is equal to 2t. So, let's attempt to sketch this. First, if t is 0, we get x is 0. Y is 2, and z is 0. Oh, oops. That was supposed to be y. So we get the coordinate 0, 2, 0. In fact, I'll write that out. If t equals 0, then we get the point 0, 2, 0. What happens if t equals 1? Then we have the point 1, 2 minus 1 is 1, 2 times 1 is 2. So we get the point 1, 1, 2. So 1, 1, and then up 2. So we get some point here. And if t is 2, then we get 2, 0, 4, just by plugging it in. Okay, so 2, comma 0, comma 4. So this is 3, 4. So this gets up to about here. And so we have this linear equation through those 3 points. And so we have sketched our linear equation. This is coming out of the page and up. And it's going back into the page and down. Okay, so let's also try to sketch this second graph. Well, this is actually quite a bit easier. First off, we're only dealing with a two-dimensional vector valued function here, but also this is something we are very, very familiar with. So let's rewrite this in terms of our parametric equations, right? This tells us that x of t is equal to cosine of t, and y of t is equal to sine of t. This should look very familiar, right? We have an equation, x squared plus y squared is equal to 1, which is our unit circle. But we might recall that in this case, if we wanted to convert to polar coordinates, if you recall doing that in a previous course, then we found that x is cosine of t, or cosine of theta is probably what you wrote, and y is sine of t, or sine of theta is probably what you had used previously. But it doesn't matter what variable we use, so we have t here, so x is cosine of t, y is sine of t. And again, this is just the equation of a circle of radius 1. So these parametric equations defines a circle of radius 1. So we've sketched our vector function r of t is equal to cosine of t, comma, sine of t. And that's it for that sketch. I'm going to do 2 more examples here. First off, the helix. Sketch the graph defined by the vector function r of t is equal to cosine of t, sine of t, t. So the only difference here, if we notice this looks like example 2, where x is cosine of t, y is sine of t. The only difference is that we get z is equal to that t value. So now we have this circle, sort of, but in 3 dimensions. And the z value is changing at each instance. So if we look directly down, if we could think about what this graph would look like if we looked directly down on top of the z-axis, or from the z-axis straight down onto the xy plane, all we would see was the x and the y values that would look exactly like our previous picture. The difference now is that the z value increases as t increases. So what this actually gives us is a helix. Using a dotted line here for below the z equals 0 plane. So we get a helix. This should actually extend out to the same point out here. That should be straight up and down where that line meets. Okay, so actually what we get is a curved helix here that keeps centered around that z-axis. Again, if we looked directly down, we would see this circle of radius 1, but this curve is actually increasing as t becomes positive and, of course, decreasing as t goes negative. And again, that gives us this helix shape. All right, so as you can see, this is getting a little bit more difficult to draw already. Even though we can understand what's going on, the actual drawing is more difficult. Example 4 is going to be quite difficult to draw. In fact, I can almost guarantee you I'm not going to draw this successfully. We're going to attempt to do that, though. But really what we want to do is we want to get an idea of how to describe this so we can kind of see what's going on in our head, but also be able to describe algebraically what's going on. First, we have x is equal to t here, y is equal to t squared, and z is equal to t cubed. Okay. So, what does this tell us? Well, we have let's actually do this. Let's just draw what's going on with x equals t and y equals t squared and ignore the z is equal to t cubed right now. If x is t and y is t squared, then we can rewrite this as y is equal to x squared, right? Because x is t. I just replaced t here with what x is. Or, sorry, I replaced t with x because that's what it is. Well, y equals x squared. In 3 dimensions is this parabolic cylinder that we had done before. We have graphed this before. Right? So we have that parabolic cylinder. Okay, now let's think about what's going on here with x and z. Well, here, this tells us that z is equal to t cubed. So, if we just do the x, z cubed, I said this wrong. Z is equal to t cubed, which means z is equal to x cubed, because t is x here. So what that means is we get if we look in the positive, for when z is positive and x is positive, we get some cubic equation here. And if we wanted to draw the negative version, we'd get some negative cubic going off of each of these. So going down and behind the y-axis. But if we just think about the positive version for a bit, we get some shape that looks like this, which would be, again, just like the front part of some like folded sheet. It's hard to show this on this video. But we get a front part of a cubic equation here. And of course, we get that for every value of y, so we can just run that along. Now, with all of that said, what is this line? Well, this line is the intersection of this parabolic cylinder with this cubic cylinder. So you would have to imagine the line that is on this picture and on this picture over here. I'm not going to attempt to draw that all into one picture, but again, this curve is going to be the intersection of this and this. So I believe that's where we will end our first video. There's actually a lot more to do in this section, but the rest will not be sketching. So we're going to stop this first video here.